All right, good morning, everyone. I'm happy to introduce today's Institute for Quantum Studies seminar speaker. We're very happy to have Alessandro Braggio visiting us from Italy, from the city of Pisa. Ale is a friend and longtime collaborator, so we're really happy to welcome him here at Chapman. I think this is the first seminar given in this room, so you have a very special honor to give today. I'll give a brief introduction to Ale. So he did his degree in the University of Genoa in 2003. And then he went on and did a postdoc at Institute in Karlsruhe with Professor Schoen. Also a postdoc at the University of Bochum, and again at Genoa University. And he had several other appointments, and now he's a member of the NEST Institute at the Laboratory Scuola Normale Superiore in Pisa. So today's going to tell us about thermoelectricity and hybrid superconducting quantum systems. So happy to turn the time over to you, Alessandro.
Okay, thank you, Andrew, for the nice introduction and to give me the opportunity to present this thinking about maybe this some results that I wish to, in a certain sense, I have the feeling I always want to discuss something done more recently, but in the end, the looking perspective, I make a question, I get a bad answer, and I say, okay, I will present that. So I make this question. How many of you knows the concept of bipolar thermoelectricity? 1, 2, 3. Okay. Okay, that's not bad, better than the usual. So I will be a little bit more faster. Okay, so indeed I have the duty that I think that is something that for me at least I would like to know before that there was this possibility. And so because typically you are not educated to that because it was discovered 2 years ago officially. So essentially, so I wish to tell about this. However, question. Okay. Okay. Is it? Okay. I need to thank all the some of them, not a complete list, but they say the most recent one. Let's say the last 2-3 years, and essentially there is Francesco and Andrew that are senior level, and also Fabio. We collaborate, and after the others are student, postdoc, PhD, and so on. And also there is Sebastian Bergeret, Michele, you know, Vivek and Lalok, Liliana, Rafa, Bion, Luca Chirolli. So these are, let's say, the people I collaborated in the last few years. And some of them was involved in this research that I present you. Why we want to investigate what we do at Pisa. We do quantum technologies, nanotechnologies, essentially. And here I present two examples. Okay, the recent years we studied the concept of Josephson phase battery, where you use a nanowire to generate a sort of battery for the phase, using the fact that you have a ferromagnetic, let's say, ferromagnetic system, okay, that localize a local magnetic field, and this generates spontaneously a phase difference, similar to the anomalous effect, but you see that you can control with the magnetic field. Here I present you a second example where is a metallic supercurrent field effect transistor. Essentially, you use 2 gates to suppress, this is the superconductor, to suppress the superconductivity in the bridge. That's really weird. There's a lot of discussion. So, which is the physical mechanism? I think that the total explanation for all the possible observation is not yet done. So this is still, I think, theoretical open problem. Still, we start to use it. So we are making device with that in order to say, okay, maybe we cannot explain which is the mechanism. If we start to use it, sooner or later we will explain it. So it will be more pragmatic. Okay, now the question is that why you want to discuss about superconductivity in quantum system, and especially I show you two examples in superconductors. And the reason I want to give a motivation that is we need new computing platform. And the reason why is quite simple. There are different types of reasons. The first is that nowadays the electrical consumption is of high performance on computing center is between 1 to 1.5 for the world consumption. This is a lot, but things will be soon war. Cryptocurrency is a really massive use of energy. It's really energy intensive. And even more, artificial intelligence will spend even more because there is prediction that between these two technology could be that in the 2015, 30% of the world consumption was done in that. And this is something that we cannot afford. I mean, that's definitely clear. Okay, you cannot spend 30% of the energy world consumption in that. Okay, because we have too much pollution and it's not justified. Okay, so we need, and there is another reason why, because also qualitatively, artificial intelligence will change also the quality of the consumption. So the research that we do with the artificial intelligence is typically more energy intensive. Okay, so we need to solve this energy issue. However, some of you maybe think that, okay, maybe it's a problem with the climate change, but I like the hot weather. I like the desert, I like the good climate. So maybe here in California, maybe it's not good, but however, there are some countries that could be good, okay? Why not? Not Italy, for example. But however, there is also another reason. If you are concerned by US security, I think that you should, okay, this is a prediction, just to say, last year prediction, 1.5 mega servers, and this consumption is 86 terawatt. This is the consumption of the Finland in 1 year. Okay, so can you imagine? I mean, can you imagine how much energy is consumed in that? However, I say climate change may be not a particularly important issue. However, the security of US could be an issue. And this is an important point because huge amount of the semiconductor done on this server is done in Taiwan. And this is the main reason why there is a conflict between China and US. That is no discussion. There is no discussion. This is the main reason. And in order to change substantially this number between 90% to 80 to 70, you need at least 10-year program and spend more than 100, 200, 300 billion of dollars continuously. Okay, so it's not just a simple things. And so in the end that we are scientists, so we need to solve the problem. And this is our problem. So we need to provide soon as possible new computing platform that is based on different technology, okay, not semiconductor, okay, possibly, and that goes fast and it consumes less. And this is why superconductor is a good option because superconductor are a good possibility because we have both the quantum, let's say, computer, let's say, hope, and on the other side also there is a possibility also to look, even if I think that there is not enough investment in this direction, in the superconducting classical quantum computing, that I think that is still something that should be on the track, okay? And still, because the consumption of the single slot in a superconducting quantum computer, in principle, would be 10 to the minus 17 watt. It's almost nothing, okay? So this means that if you are able to build a classical supercomputer, even classical, it could cost much, much, much less. But still, there are some problems. And the problem is that you have still problem with the material design. For example, for the quantum computer, still is an issue of material, essentially, because we can get, you probably are more expert than me, it's enough coherence time, or at least in a platform that is, can be scaled with a huge number of qubits. So large-scale segregation is a problem. And there is this point that is exactly you have to keep at the low temperature because you want to keep a long clearance time. But on the other side, it's called to keep it at sub-Kelvin temperature, those type of system. It costs for each watt extracted, you spend 1 megawatt. It's the most inefficient refrigerator of the history of the world, 10 to the 6 fraction. So this is really something that, so any single amount of power that you save it or that you are able to use it at that sub-Kelvin temperature give you a huge advantage. So especially you can imagine if you increase the number of Josephson junction or qubits to billion, this will create a problem, really no overheating effect. And essentially it's the same problem of classical quantum computing. So the same problem and the same, and in a certain sense you need to think, and we are hardware like per persons, so we want to solve the problem on this side. So how to make an efficient heat management of quantum circuits. And the point is that now I arrive to the crazy point, because superconductors are the worst, let's say, thermal material, because it's a thermal insulator, actually, especially at very low temperature. So it seems a very big point. Remember that in semiconductor, the big advance in technology was the changing from the pure semiconductor to introducing copper, okay, in the circuit, because it was able to, the copper is much higher thermal conductance. It was able to get out all this power, okay? Here we have a thermal insulator. So you are even in the most crazy position to solve this problem. And not only say, maybe you can try to use thermoelectricity and get started for another problem, but it's a particle symmetric system. It will exclude the thermoelectricity if you think in a simple way. So it seems crazy, but it seems that you are in a big problem. And so I would say, and I hope to convince you that in this talk that thermoelectricity instead, I think, that the superconductor are the best thermoelectric material that we have, okay? This is really strange, but I think that is the case. And the history of the thermoelectricity and superconductor is quite long. It starts from a paper by Meister that say, okay, look, in the superconductor, you have something that is zero resistance. So if you apply, even if you apply gradient of temperature, you get essentially, you cannot develop a difference of voltage. So this equivalent to say there is a shunting effect and there is no thermoelectricity at all. That's completely clear. However, things, as usually happening with superconductor, are a little bit more subtle. And Gisburg did this wonderful paper in the 40s, essentially, where he predicted this thermophase effect. Essentially, if you say, okay, but okay, even in superconductor, you have a quasi-particle state. Quasi-particle states, they behave similar to a simple electron states in a metal. So essentially, for those states, you can get thermoelectricity and you can get Jn. And after the system reacts, generating sort of Josephson current that goes in the opposite to compensate. And so in the end, the gradient of temperature will determine the difference of phase. This is called thermophase effect, and it was even measured, okay? Essentially, in the 70s, they start to measure, there was some problem. Everything was fixed in the beginning of the new millennium. Essentially, so those effects, however, this effect is small, This effect is quite small because it's based on the intrinsic thermoelectricity that you have in a normal metal. In a normal metal at low temperature, okay, you can imagine that in a normal metal at the room temperature, typically you have a seebeck effect of the order of microvolt on Kelvin, and now you go 300 times less. So it's very weak thermoelectric effect. So in a certain sense, you say, okay, no, probably thermoelectricity is not a good resource. However, surprise, maybe, okay, I don't know many, certainly, Andrew, yes, but how many of you work with the thermoelectricity? 1, 2, okay, 3, okay. Okay, essentially, what is thermoelectricity? I want to be simple, nothing really fancy. I assume that you have a material with 2 different temperature, okay? Could be even 2 different material divided by a sort of junction that as we will consider. And you can assume that due to the fact that you create a difference of temperature, you generate a current or a voltage and around the circuit. And so you can compute using the quantum transport because we will consider some coherent system, let's say. And you can define the figure of merit that typically is the Seebeck coefficient. That is nothing more than the voltage difference that you generate at your system due to the gradient of the temperature. This is essentially this basic quantity, it's a linear quantity. And you can compute it using this formula, and you realize that it is given by this formula essentially, where it is important to note that essentially, due to the fact that the numerator depends on the derivative of the Fermi function, and there is also an energy here, this is even, this becomes hot. So it means that in order to have a non-null result, this should be odd in around the Fermi energy to get an effect. So essentially, and this is the point, Say, because typically in a superconductor, I mean, is even, you have particle symmetry, this is even, and it seems that you are lost, okay? I be more specific. So for example, here you put in your quantum transport equation, you put some tunneling matrix element that has this shape that contains the information about the junction and the information about the density state of your lead. And now you assume to take a more simple junction, so an energy independent junction. And so you see that we have energy dependent density state. And now if you have a superconductor, you have this symmetry that is called improperly particle symmetry, okay? And due to symmetry, you are lost because you cannot have thermoelectric effect in the linear level. This is the point. And
it's true also for metals, right?
It's roughly true also for metal. Indeed, the effect is very small because this is true also for metal around the chemical potential on the neglecting order of T over Tf. So because you need to have a little bit of curvature of your spectrum. So with Francesco, we started to investigate this type of problem with the thermoelectricity in the Josephson junction, but starting from a different perspective. At the time, we was exploring the ferromagnetic superconductivity and blah, blah, blah. Okay. In the end, we realized the following argument that I will show you. That is probably the most important. Okay, if you don't know about the bipolar thermoelectricity, this is the most important slide. Okay. Essentially, you have a superconductor insulator superconductor system, so SIS. And let's start to assume that you consider the case of identical gap. If you assume identical gap, you have this type of scheme where, please note that I assume to put temperature finite here and zero temperature here. I want to be extreme, okay? If you do that, you realize that here you have some quasi-particle state, quasi-Hall state. But now what happened is the following, that you realize immediately that the only response that you can get from this system in this presence of gradient of temperature is dissipative. And the reason why, because if you make the computation, you realize that when you shift the chemical potential, you see essentially that the quasi-particle change, the quasi-particle tunneling change reducing, and also this reduce. So in a certain sense, what happened that due to there is a sort of exact cancellation. And this is exactly the question before. This is a completely particle symmetry system. We are just a little bit shifting. So you are in the linear regime, you cannot get any thermoelectric effect. That's it. Now, things become weirder if you consider an asymmetric system. Because look what happened. You do exactly the same argument, but you know now the following things. When this reduces, okay, you see that the quasi-particle state, you see that the density of state reduce. So now when you put the chemical potential in this direction, you expect that the current goes in this direction of a quasi-particle. And now you see that instead, due to the fact that density of state is monotonously decreasing with the energy, you see that when they go down, this density of state goes down. So in a certain sense, what happens is that the quasi-particle state reduce and the quasi-Hall state increase. So you put the chemical potential in this direction, you get the current around against you. This is a thermoelectric effect, essentially. It is, okay, now let's try to get which is the sufficient condition, okay? The first point is that you see, oh, I am even linear because I'm just a little bit shifting. So I'm linear in the voltage, but I'm not linear in the temperature. If I repeat the argument and I put the temperature big, identical here, again, there is a full cancellation. First. Second, different gap, as I said you. Another important point is, you see, is independently what is the structure of the density state here, it's not so important. What is really important is the density state on the cold side, okay? So monotonously decreasing density state on the cold side. And last ingredient, the density state shift with the chemical potential. And these all are ingredients. They are sufficient to get the thermoelectricity. They are not necessary, however, potential. And the question is that, in a certain sense, what we get this is something that can be certainly discovered in the 60s. Maybe when BCS was done, essentially there was the expression of the tunneling in a Josephson junction, and we used that expression. So it's very simple. And now let's see what is this, the linear regime. So we are in this situation. So indeed, you see that in this case, the red curve corresponds to the thermoelectric behavior, and you see a negative slope. Negative slope means thermoelectricity, and you are in this part because essentially the product between current and voltage is negative. It means that you are producing power, right? Because typically you put the convention that is positive IV corresponds to dissipation, and this is thermoelectricity. However, you see that, okay, what happened? Now, if you increase a little bit the voltage, the working point, you can arrive to the maximum. This is a configuration of the maximum. So we can also find which is the maximum thermoelectricity. It is the matching peak, essentially, the value of the matching peak. You see that the linear, in the case of equilibrium, you see there is this peak, okay, this peak. But in the case where you configure to get thermoelectric effect, you have this negative peak, and this negative peak is the thermoelectricity. Okay, so this is the nonlinear, as a sort of nonlinear thermoelectric effect. However, there is another point that for me was the most puzzling point when we discovered it, and this is the following. Is the following, that due to the fact that you have this particle symmetry in the density state on each side, you can demonstrate that your ID is reciprocal. So it means that at this symmetry, odd symmetry. And this odd symmetry is weird because look what happened, look what does it mean. It means that if you have, okay, you can typically in this type of system, and what you do, you look where the, let's say, you look at the seabed voltage, what it is the voltage that you get in your system given a certain gradient of temperature. And this corresponds to this point, okay? But you see there are 2 points. So it means that you have a system with a gradient of temperature, and you can have 2 different opposite voltages. And this is something that for me I was stuck in. Honestly, I'm a theorist. I worked in a little bit in thermoelectricity, and this is something that struck my mind because this is something that you are not expected. Because in a certain sense, it's something that is strange. Typically, your systems that are P-like, N-like, or P-like, and they get different type of behavior. But this is something that can be both P and both N. On the other sense, you could say, oh, might be not completely crazy because I'm a superconductor. A superconductor is particle symmetric. Why cannot be both P and N on the base of certain spontaneous breaking of symmetry? And this is exactly the point. I stopped the work. I stopped for 6 months of publication because I want to be sure. And after we did also the analytics, so I was sure that it was that. So it was not a joke. And here you see also another important point, that you see that this is, I'm changing the temperature of the hot lead. And this is hotter than this. But you see that this is dissipative. And this is become thermoelectric. So essentially, you see here the nonlinearity of the problem. So because in a certain sense, you are increasing the thermoelectric effect, the gradient, and you get at a certain point that the thermoelectric effect disappears. Okay. So things are weird, okay? But for me, the most striking point is exactly that the bipolar thermoelectric effect, and after if you compute the Seebeck effect, the nonlinear Seebeck coefficient, it's really huge. And so you say, okay, this was the theory. Okay, now can we do the experiment? And we did the experiment. We did the experiment, and was hard, but not extremely hard. Maybe the most difficult part was try to find a way, because I forgot to tell you that in this type of analysis, I just forgetting the Josephson coupling. So I need to create a system without Josephson coupling. That is really bit strange because a superconducting tunnel junction typically are done to make important the Josephson coupling. No, you need to build a system that the Josephson coupling is suppressed. Are you telling me, oh, but this is particular state? Not enough, not really, because you just need to suppress a little bit the Josephson coupling and you get the effect. So it's not, you need to know to bring the Josephson coupling to 0. You need to bring Josephson coupling maybe to the 30% of the original value. So it's not a crazy problem, okay? And this is the experiment. And here you see again the important point. The solid curve are the IV, the measured IV curve for that for the system. And here you see the different color corresponds to different power in the heating. So we make an heater on one side, we start to increase the power on the heater, and this we create a sort of gradient. And you see that this reduce with the increasing the power. That means that you are increasing the gradient at a certain point, the thermoelectricity goes down. Okay, so in a certain sense here you see the nonlinearity of the effect. That is a little bit unweird, but in a certain sense for us was the confirmation that is that effect. And in the dashed line, you see the comparison with the theoretical analysis. Okay, so the analysis was good, and also the prediction that we did was good, because in the original paper, theoretical paper, we predicted this value, and we get it. Essentially, we get this value, essentially. And here you see, which is and here you see, indeed, there is a bipolar effect. So you see two different Seebeck coefficients. So the system spontaneously developed two different Seebeck coefficients. And you can do some game on that. Okay, for example, you can do something that you cannot do in a classical level. So you can, in a certain sense, your junction is not even neither P, neither N. When you polarize, become P, or when you polarize, become N. So for the thermoelectric effect, it's crazy because you can do many more game. Okay.
Maybe a question here, Alex. So often when you have this kind of hysteretic effect in magnets, you have some kind of instability, you have like a bistability jumping. Do you see this kind of effect as well?
Yeah.
Okay, good. All right, good.
Indeed, with Francesco, I was telling him, look, we have measured an IV, but the IV is done with a generator that put your voltage, fix your voltage. And now the question is this real thermoelectric effect? Who cares? I mean, you say the people could say, I don't know, but you are putting a really big generator. What you are doing, I don't know. So I tell him, no, look, we need to demonstrate that the system generates power over a load. And this is a thermoelectric effect, okay? And so we put this configuration. And after we obviously realized that we need to put a current generator here, because you need to polarize it. I told you that is or P or N, but depends on the polarization. So we need to polarize and after release. Okay, and if you do that, you need to charge it and after go 0. And that you charge it and after you go 0 and you stay here. And after you push against, and now the system react against the generator. And at a certain point, you're not anymore able to do it, and you get this hysteretic cycle. When I was saying that, no discussion. This is spontaneous symmetry breaking without by definition, okay? Because it's by definition. And yeah, and this is the comparison between the experiment and the theory was quite good. And this also, we did also a patent on this because it is a sort of volatile thermoelectric memory and so on, okay? Okay, now the point is that we have demonstrated the fact, so what we can, which is the characteristic of the effect. For example, if we put a single electric transistor done by a superconductor, insulator, superconductor, insulator, superconductor, and we put this configuration of temperature, what happened to this effect? In this case, you will expect that you have charging energy that enter in the gate. So it means that with gating, you can modulate the thermoelectric response. And indeed, we did it, we computed it, it's quite easy. And you get this picture that seems, this is, let's say, dissipative behavior. If you look here, there is a little bit of fancy yellow things and fancy blue things. Maybe you don't see here too much if you make it. But if you make it cut and zoom, you see that this is dissipative, here become thermoelectric. So the system also, by changing the gating, you're going to bring in a place where the system becomes thermoelectric. And the mechanism is essentially the same. The only difference that now you're using the charging energy to manipulate it, essentially. And here you see the IV curve as a function of the different gating, and you see that you can manipulate the place where the system becomes thermoelectric, essentially, by Coulomb energy. But for me, this, in a certain sense, for me, was a little bit boring as a theorist, this part, because I mean, I have all the things, I know how to compute it, and this is the result. Okay, and for me, it's not nothing that I learned. But to be completely honest, I was very happy to this paper because I was able to demonstrate something that I told you before by intuition, but I was not able to demonstrate mathematically. And now I was able to do. Because essentially I told you that it's an important point, and then this is important, that the density states shift with the chemical potential. This statement, it seems, if you look at BCS theory, it seems obvious. I mean, it's a BCS theory, okay? But in the BCS theory, it's telling you something that is an interacting theory. Because look, you open a gap around the chemical potential. So this means that you are demonstrating the bipolar thermoelectric effect is a consequence of the fact that the BCS theory and it's a mean field theory of the interacting theory. That's something that it's struck my mind because it's always there, it was always there, but we never realized that. But this is exactly the point. It's actually make an argument on the rates. You can really demonstrate that, okay, if you take your rates, clearly you can demonstrate there is valid detail balance. But now, look what happens if you change the temperature of the bar of the two sides, because you can still use the golden rule. And you see that the negative energy side goes up. The people that do detail balance or the people that do, you know, this fluctuation distribution theorem and blah, 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 they should immediately say, oh, come on, but this is the negative energy state become much stronger than the positive energy state.
Sorry, what are you plotting in this plot?
This is the rate as a function of the energy.
Which rate?
The rate is the tunneling rate.
Gamma.
The tunneling rate as a function of the energy. And you see that this is equivalent to say that you have a strong violation of the detail balance. Really strong, because you have the negative energy state is bigger. In a certain sense, in the thermoelectric system is obvious because you need to push the electron against the gradient, no? Okay. But in the end, this is what struck me. And you immediately see that in order to get this strong violation, you need to have a density of state that shifts with the energy. So you can do a mathematical argument that show you that essentially the only way to get it is to assume, because if you don't put that, you don't get effect. So essentially here demonstrate clearly that what I was imagining and also what you can imagine, because if you have a spontaneous symmetry breaking, the spontaneous symmetry breaking is an interacting mechanism. So in the end, you have also these things. And now we was able to demonstrate that is due to the interaction that is inside the BCS, no discussions. Right.
Isn't the detail balance known previously like to break when you have energy dependent transmission?
Certainly.
That's not
when
new,
you have
right?
a gradient of temperature, we are not in equilibrium, so you break the detail balance. But what is subtle here that you need to do this strong violation. It's not simple evaluation, it's a strong violation. So the negative energy state should be bigger than the positive. Yeah. Okay, so interaction method. And now we play with it. Okay, for example, I discuss you this issue about the heat management in the quantum system. For example, okay, using this type of system, you have a natural thermal diode. The people that study thermal diode, you can find that. But you clearly have, even in the thermal part, you have a completely an asymmetric behavior, first. Or what it was for me for intriguing is that you can do heat piping with electricity. It's clear. The thermoelectric effect is still a thermodynamic engine. So it's clear that the power that you produce, okay, is taken out from the gradient. So it's clear that what you can do, you can do in a sort of heat piping. So you take out using the thermal gradient, you generate power, electrical power. Using superconducting wire, you can bring this electrical power far away. So this is can be very advantageous. And this effect is not small, not at all small. I tell you that we demonstrate that, so you can do some math, and you can demonstrate that you can produce at sub-Kelvin temperature, so I mean less than 1 Kelvin gradient of temperature. You can generate in a small piece of superconductor of 1 millimeter square. You can produce the power to switch on at room temperature a LED. You know the small LED that was in the old Macs, a small one. But it's a huge energy. I mean, you don't know when you go down in this temperature, the coupling, the electron-photon coupling goes down as the T to the 5th. And so any small energy that you can take out is a big advantage. And this is a very strong effect. It's a 40% efficient in terms of thermodynamic machine. So it's a strong effect. It's not small. Now with Francesco, we are trying to build a really big one, a big junction, because those junctions that we did in the experiment was very tiny, was 1 kilo. Now we want to go to 100 ohm. It's a big story, and actually is also big educational story, because you know which is the main problem in the thermoelectric effect. The thermoelectric effect is not a problem to get a good Seebeck coefficient. In the thermoelectric effect, if you go to speak to the people that do that, the real problem is to keep the gradient of temperature sufficiently high. And indeed, in a certain sense, this explains you why this effect is so strong in the superconductors, because in this type of junction, you create the higher gradient in the universe, because you create 10 to the 9 Kelvin per meter, because the barrier, the thickness of the insulator is 2 nanometer, and the gradient is of the order of the Kelvin, 10 to the 9 Kelvin by meter. So it's a huge thermal gradient, and you can do that because you are working with electronic degree of freedom, and the system has all the same temperature on the phononic degree of freedom. So in a certain sense, it's the ideal thermoelectric effect, because the electronic degree of freedom are higher temperature, but the phononic are all the same. So there is no heat flow to the phononic channel. And this is the advantage in a certain sense, maybe also the limit in a certain sense. Here, for example, we will show, okay, let me know how much it's done. Okay. Here we show what happened, for example, because when we did the experiment, in the experiment, we need to create a junction with different gaps. Now, the most simple things that you can do to the experiment is to create a bilayer, so superconductor normal metal bilayer. By using inverse proximity effect, you reduce the gap of this. And in the experiment, we did that exactly, and using aluminum and copper, I think. Copper, yes. And now we did this type of junction. And because for us was obvious that, certainly is this the good one, because here there is a superconductor, so I would expect that the density state is very peaked. However, things are not so simple. If you make the computation using this user equation, you can compute this configuration, and you see that the inverter configuration is even better. So in a certain sense, probably in our experiment, you remember that we get this type of smoothing curve, okay? Probably the smoothing curve is due to this fact that we choose this geometry instead of this, probably. And so you can even increase a little bit, changing the way you do the junction, the geometry, and now we have the full control even of the thickness. So in a certain sense, we have a little bit more control of how to produce a good bipolar thermoelectric effect. I want to show you another possible application because it's inspiring to me, and actually I'm working for a different reason on this type of problem. Essentially, you have this bipolar thermoelectric effect, you assume to shine an AC driving in this. And you can do photon-assisted tunneling. And in this photon-assisted tunneling, you see that you have this single, let's say, peak of the bipolar thermoelectric effect and become split. Okay, this is the case, there is the dissipative part. But okay, the dissipative, the matching peak will be shifted by the sideband. Okay, essentially, this is what you expect for the photon-assisted tunneling. And you say, it works also with thermoelectricity? Yes. It's funny, because look, it means that in this place here, you are just bringing the, let's say, the thermoelectric capability here in a different point. And in a certain sense, you have a system that hybridizes where the photons helps you to get thermoelectricity. Okay, so in a certain sense, you get the photon degree of freedom that helps you to get thermoelectricity. I want to say that I cannot say too much because it is still ongoing work, but I'm telling you that this can be even more deep. In a certain sense, here you have a situation where the photon helps you to get the thermoelectricity. However, the question could be, in a certain sense, you could say that you can increase the thermoelectric capability of the material. No, because if you compute, in a certain sense, the thermoelectric power that you generate in the IV curve, in a certain sense, the area beyond this peak is always bigger than the area between all these peaks. So in a certain sense, the global thermoelectric capability is reducing, not increasing. So you're just redistributing this capability in different energies, at different energies. That's the point. However, I'm telling you, this is part of the story. There are situations that you can generate thermoelectricity where it's not big, okay? But it's not so simple, and I hope the next time that you heard about me will be for that. Okay, some other possible application. Broadband single photon detection. You have a system where you get photons, this become hot, so they create a gradient of temperature, and this generate a voltage bias. This is a detector, single photon detector. You can evaluate which is the performance of these single photon detector. You see there is very wide range. So it's a wide range single photon detector with a good signal to noise ratio. And here you see you have a different material. We also patented this. Okay. Good. No, this is one to discuss about this. So probably we are all to the closing. Just last point. Until now, I always discuss a system where they are all superconductor. But at the beginning, I told you one thing. Look, what is really important is the cold side, that you have a density state that shifts with the energy. But I don't discuss too much about let's say, the hot side. The hot side, the only important things of the hot side, there is a gap. And if you get a gap, you can do this gap not with the superconductor, you can do with the semiconductor. And in this case, for example, we decide to use a bilayer graphene. In the bilayer graphene, it's funny because you can, using the gating between these two, the gate here, you can shift, you can open a gap. And so you can open a gap and you can compute essentially between this type of system and the superconductor, what happened to the thermoelectric effect. The superconductor is kept even cold because it could be even at zero temperature. So the only thing that you need to make hot is this part over here, and you can use ohmic contact to make it hot. So in the end, you can create a very big gradient, even more than before, and work in a higher temperature. Essentially, you can work at 10, even up to 10 Kelvin here. And in this case, so if you make the computation for this type of system, it's very similar, and you get this type of IV curve where you see still you have the bipolar thermoelectric effect. So this demonstrates that you don't need just two superconductors, but just only one. And it tells you also the strength. So the effect is quite strong because it could be on the order of 1,000 microvolt on Kelvin, on the order of Kelvin temperature. So, and also here was able to demonstrate, because in this case, you can, using this gate, you can shift the chemical potential, because this is a semiconductor essentially. Instead, in a normal metal, no. In a normal metal, what you change when you change the density of the electrons, you change the chemical potential and the gap open around it. But for the superconductor, for a semiconductor, instead changing the gating, you can move the chemical potential in the band. Okay, this is the big difference. And so you can compute the effect also in the presence of moderate breaking of the particle symmetry. And you see that with the moderate breaking, it still works because it's a spontaneous symmetry breaking. So there is another factor that is the interaction that is in a normal metal, that is a huge amount of power in a certain sense that you have at disposition. So even if you moderately break the particle symmetry, you still have the effect. Okay. I think that okay. Here I want to just quote some, just the last point. Up to now, I show you an effect that is the bipolar effect and some possible application. However, thermoelectricity at low temperature, I think this is interesting also as a detecting method. And during this year, so we're working on that. And we realized that doing, for example, non-local thermoelectricity is a very clever way to get information about the helical state, because essentially here you have a situation where really you see clearly that even if you have a system that is particle symmetry, you can have thermoelectricity, because this system is fully particle symmetric, but you can have this thermoelectricity because indeed the real symmetry that you use in the thermoelectric effect is the symmetry between positive and energy state. Instead, the particle symmetry is a different thing. Particle symmetry says you that is an electron that goes in this direction with spin up, goes in a hole that goes in this direction with spin down. So change the direction. So in helical state where the spin is connected to the direction, you can get this difference and you can get thermoelectric effect. This type of idea can be used to detect, for example, also Bogoliuba Fermi point. That is a different problem, let's say. We did also recently some work on that. You can use to identify order parameter symmetry. So it's a good detector, especially when you play with superconductors. So it's something that the people do not expect, but it can be useful for many, many different points. There is, I should quote clearly, the fact that I think that you are very aware that let's say we recently published with Andrew and Harlock and Vivek concerning there is this figure that is, okay. And in this effect, essentially you have a vortex, okay, and the Navier-Stokes vortex. And the funny thing is that you see that you have it's another example essentially of this argument, no? Because which is the particle symmetry in a vortex, you have all particle state with positive energy goes in electron particles, in all particle state with negative energy and go in the other direction. So this is why the vorticity, in a certain sense, at the center of the vortex, you break strongly the particle symmetry, and this generates a huge thermoelectric effect. Okay, and this is something that we hope also to use for something more practical. Okay.
Millivolts per Kelvin.
Millivolt or Kelvin, sub-Kelvin.
Not microvolts.
No,
millivolts.
Yeah, this means, yeah, indeed, that's exactly the point. That's exactly the point. The superconductor is funny because it seems that you say something crazy because you take a material that is few microvolt on Kelvin at room temperature. You go at you reduce the temperature, typically the Seebeck effect scale with the temperature. So you reduce a factor of more than 300, around 300, and you get an effect that is 3 times more. I mean, 100 times more, 1,000 times more. This is crazy. I mean, this is really crazy. It's a crazy thing. Okay. I was just to advertise you this work that we have recently done. That is again thinking to the problem to the detection, okay, thermoelectric detection. Essentially, in this system, we want to compute which is the heat exchange by interaction, okay? And you use this thermoelectric, this system. So important that you get this picture. This picture is saying that it's a nu equal to, so 2 channel, and you have this configuration that you can get non-local. This is hot, this is cold as this.
Maybe you should say this is a quantum Hall system.
Yeah, it is quantum Hall. Absolutely, yes, quantum Hall system. Integer quantum Hall. And actually you see that if nothing happened here, you see that this is cold from the cold side, arrive to the QPC. So in principle, QPC is a material that can give you thermoelectric effect. However, this has the same temperature, so no thermoelectric effect. However, this is hot, and this is an electron that goes nearby to this. If there is a heat exchange by interaction, okay, you can bring energy over here, and this generates thermoelectricity. So in a certain sense, the local measurement of the thermoelectricity is a direct measurement of the heat exchange. Okay. The funny thing is that with the integer quantum Hall effect, using the bosonization, you can compute this. You can fully compute this problem that seems quite difficult because you have an interacting effect out of the equilibrium. However, with the bosonization, you can do that. I want to do the long story short, but the idea is that you can solve it. You can write in terms the electronic operator in terms of bosonic or phase field. And this phase field is a couple system of equation of the phase field can be solved. I mean, at least when you have a local interaction, you can easily solve it as a combination of symmetric, anti-symmetric mode of the phase field. And in the end of the story, essentially the physics is driven by charge mode and neutral mode. And these 2 modes, if you have some interaction, as usually you want because you want to speak them, you assume that in this system there is no electron tunneling because it's done on the scale that in quantum Hall the mean free fluff is around 310 micrometer. This is on the scale of 1 micrometer. And so in the end of the story, you see that this charge neutral mode that determine the physics of the system. And I want to give you, I don't want to enter in the details where we compute this sort of bosonic methods, blah, blah, blah. We compute the cross correlator. This is something that I don't want to discuss this. Okay, this is interesting because using this formula, you can provide in a certain sense an exact writing of the energy current, exact in terms of quantum operator, okay? We can write the quantum operator for the energy current. You can compute it, and in the end, want to discuss this, you find this, okay. Essentially, you see here, there's the outside, both sides, and the colloid, the dashed colloid, the solid is outside. And you see that you have a scale that is given by interaction where the system starts to change energy. And this, you can compute exact in terms of effective temperature, essentially. And you see that the interaction will bring you exchange of energy. And after the system equilibrate to what? Equilibrate to what you expect is the energy equilibration of 2 Fermi systems that goes in contact. Okay. And this is something that is clear, and then you get it, and it's clear that you should expect it because this is guarantee you that you see the thermodynamics is fair. So it's in a certain sense the effect in the end is dependent by the interaction, non-equilibrium, blah, blah, blah. Thermodynamics works. And this is because this is required by thermodynamics. Okay. And here you see, which is the scale, the disequilibration happen, and you can compute in a sort of, by measuring the temperature, you can measure exactly the exchange. Now, clearly in our idea, we use this thermoelectric device to measure this. I don't want to tell the story, it's quite long because you can compute even a case where you have a cross correlation, you can suppress or not the cross correlation, so you can see how the electronic distribution change depending if it include or not include the correlation. This, if you are interested, go in the paper. In the end, you see that the thermoelectric effect is exactly a measurement of the heat exchange. So essentially, the nice thing, and this is something that is another message. Thermoelectric effect is interesting not only because it's intriguing, I think, with the superconductor and the quantum system, but it's interesting also because it's the much easiest method to study heat current. So when you have a problem with heat current, it's difficult to measure. If you go in a lab, it's almost impossible to measure heat current. You need to do an indirect measurement because you need to look how the current change the temperature over some reservoir. So in the end, the thermoelectric effect instead transforms the information of temperature difference directly in current. That is much, much, much easier. Okay, so this is why I think the message is that thermoelectric effect is good. So we arrive to the conclusion. So essentially, I hope that I show you that there is a lot of interesting things I can do with thermoelectricity in quantum technology. Local and non-local thermoelectricity can be used to address different phenomena. Okay, I mentioned to you some physical new effects on bipolar thermoelectric effects. It's usually in certain terms classical origin, but I promise you that on the scale of less than 6 months, we will demonstrate there is also a quantum version of it. Okay, and this is something that I'm working on. And superconductors are excellent thermoelectric materials. And I think that can be used seriously because this effect is not small, are big. And okay, this is an error that was on the previous. Okay, no problem. Okay, the idea that you can use also to investigate heat relaxation, heat processes in a quantum system. Okay, okay, that's it. I hope that you get at least I hope that you go out knowing what is bipolar thermoelectricity, because it's something that I wish to know before, because I lose 6 months on that. So I hope that you get it fun.
Thank you, Ale. Questions?
For the bipolar thermoelectricity, you said that you need to have a sufficient thermal gradient for it to be in the active regime.
Yes.
And if it's not sufficient, it's like dissipative.
Yes.
Do you know what exactly is the thermal gradient? That
okay, it's nonlinear effect. So in the nonlinear effect is really difficult to make a general statement. This is usually the point. Okay. So in general, we have some rule of the thumb. I think that I wrote somewhere. Yeah. This is the rule of the thumb. So essentially is something that is connected. Okay, this is the cold side. This is the cold side. This is the hot side. And this is the asymmetry, the ratio between delta. So essentially, this is a rule of the thumb. But however, this is not precise. I mean, because when you are in nonlinear effect, because the most important point is the peak. The peak is in a fully nonlinear because they have finite voltage, finite temperature difference. You have an integral, and it's hard to get analytical formula in that case. The analytical formula that I show you here, it was extremely clever because I was able to change to us making the assumption that the cold side at 0 temperature, you was able to change the shape of the integral in the way that you can solve it. But if you don't do that, you keep finite temperature, you are lost. Okay, you cannot do nothing. Okay. So unfortunately, this is a problem of a nonlinear system.
Another question. So you said on the hot side, you need a gap, and that is sufficient for the
hot side, yes, sure.
In the cold side, it seems like if you have a non-uniform density of states.
Yeah, okay. The request on the cold side, you see, okay, the request on the cold side, you have negative decreasing, but if you have, for example, if you have a Coulomb effect, the Coulomb effect, you have a peak centered in the chemical potential, it still works, because here you have a peak.
Yes, and it moves with the chemical potential as well.
Exactly. That is the crucial point, because it's an interaction effect. Otherwise, you don't have this effect. Yeah.
Okay, thank you.
Other questions? You mentioned this possibility of generating the thermal electricity in your cryostat and then bringing the wires out to room temperature. When you do that, isn't there also some big thermal gradient between the cold and the hot that destroys this effect?
You would tell me everything. Okay, in the experiment that we did, clearly, the point is that you generate DC thermoelectricity. In the experiment that we did, we have filter, okay? Clearly, we have the really, no serious, this experiment that I show you, the resistance, what has room temperature, we change the resistor by hand. I mean, I don't joke, the resistor was at room temperature. The problem that you have this wire that goes from room temperature to zero temperature, and you have a lot of filter. Okay? But the filters works in AC, but you take only the DC component. Did the time scale of the circuit, RC circuit of this was, I think, hertz, 100 hertz. So it's nothing. I mean, it's not something that you can use in quantum technology, not to do control qubit. No. It's just to make a DC measurement. It's very good because you can get a wire at a room temperature, but extremely high filtered, you can get a down temperature. Because the point that they take out in DC.
Yeah, but there's not a opposing Seebeck effect.
No, because it's the scale. It's the scale that give you. The point is that you are telling me, okay, this is a resistor. You're telling me, right?
So even if I have a small.
Yes.
Seebeck
You have a
effect for
resistor.
metal, I've got
Yes,
that 300-degree
what they call
temperature
Wi-Fi heating. So you have Johnson liquid noise. No way. So you have a resistor at room temperature, 300 Kelvin, and another roughly resistor at almost 1 Kelvin.
Yeah.
Okay. So this corresponds to a certain heat that goes through. But the filters do exactly that. The filter reduce the bandwidth such that this power is reduced. And so in the end, the amount of power that arrived from the external, room temperature resistor is very small in comparison to the intrinsic scale. That's the point. But it is an important point. What you're saying.
Okay, let's thank Ali again. Very nice talk.